Welcome everybody to the second day of BFPV. It's a great pleasure for me to start the second day. So actually good morning, good afternoon and good evening everyone. My name is Radovan Kopeček and for me in Konstanz in Germany it's a night session. It's 11 o'clock. Today I will give you an overview about the status, about the chances and challenges of bifacial photovoltaics. So first of all, before I start with bifacial PV, let me give you some motivation about PV in general. We have total installed PV systems until now of 650 gigawatt. Expected installations in 2020 dropped down after Corona from 140 to 105 gigawatt. However, quite soon we will come to 1 terawatt in 2022 or 23. And in 2050 we are expecting about 30 to 70 terawatt. So we are just at the beginning of photovoltaics era. The module prices are now already below 20 US cent per watt peak and levelized cost of energy of about 2 cents or even below, for example, in MENA states are reached, the lowest one at 1.35 US cent per kilowatt hour. And I'm quite sure that with bifacial tracking, we will reach 1 cent per kilowatt hour or even below very soon. So now the technology, the modules are these days mostly PERC modules, however, now coming to their efficiency limits of 23%. And the cost down is these days then realized by larger wafer sizes. It seems that M10 is now becoming the new standard. But N-type cell concepts are now also gaining importance because with N-type you can go above 23 or even above 24%. These days 60 cell modules are reaching 400 watt peak for roof applications, and the 72 cell modules or equivalents are now even exceeding 500 watts. But we should keep in mind that actually it's not the size that really matters, but efficiency or power density for bifacial devices. Tomorrow and day after tomorrow there will be a webinar from Taiyang News, which will be opened by Charlie Gay. So I'm also very interested what will be reported there. Coming to the agenda, first of all, some slides about bifacial PV, and then I will look at bifacial modules. What is a bifacial module, and can we expect maybe N-type in future? Then look at the chances and challenges of bifacial PV and end up with a summary. So now already in 2017 in Saudi Arabia there was a bid from EDF and Mazda, the first one below 2 cents per kilowatt hours. But at that time it was rejected because of many reasons, but maybe also because bifaciality was not bankable at that time. But in the coming years, bankability improved, and there are more and more bifacial tracking systems popping up in the MENA states. The lowest bid so far was done in Abu Dhabi with a 2 gigawatt system, but also, for example, the second lowest bid with bifacial tracking from Total of this 800 megawatt in Qatar, which will be built before the Soccer World Championship, hopefully. So if you look at the ITR-PV technology roadmap, you see that bifaciality is gaining importance. In 2020, we will have already about 20% bifacial cells and modules, and in 2030, about 70%. But you know, we are at the beginning of PV. So in 2020, about 27 gigawatt are produced, but in 2030 already about 1 terawatt. So bifaciality will get unchained very. The status so far and until 2020, that's a forecast. So at the beginning we hardly had any installations until 2016, but then larger systems were bifaciality started, as you know, with N-type fixed tilt, then horizontal single axis tracking N-type, but also P-type cam, and now we have large systems are mostly horizontal single axis tracked P-type systems, and we are expecting in 2020 a total installation of about 20 gig. Now, history now in bullet points, more or less what I said already now, but in more detail, is that in 1950, the very first cell from Bell Labs was a bifacial cell, actually an N-type IBC, but bifacial. Then the polarity had to change because of space PV, so everybody went to P-type because N-type was not stable in space, and that is how monofacial PV was born, because of the very beautiful aluminum back surface field formation, and it was very nice that the aluminum was not only forming a contact but also more or less passivating the rear side. But then the passivation was not good enough, and since 2000 there are many groups working on N-type low-cost bifacial cells, including us. And then bifaciality slowly was then entering the PV market, the terrestrial market, for example in 2013 with the first large megawatt system in Japan. But what was very important for bifaciality then, that PERC actually came on the market, and PERC was also made bifacial from 2016 on. And I would say that was the big breakthrough. So bifacial PV was becoming big with PERC. But what is happening at the moment is that PERC is coming to its efficiency limit, as I told you before, and now costs down are done now via wafer sizes. So N10 is becoming the standard. People are asking what will happen with N12. So now N-type concepts are gaining more and more importance because of higher bifaciality, but also because of lower degradation and lower temperature coefficient, because of higher voltage. But what is happening now as well is that gallium doped wafers are entering the market very quickly. So this could be an additional boost for PERC solar cells. But anyhow, if N or P-type, the future belongs to bifacial modules with a high power density. If you look at the bifacial installation spread worldwide, you can see that most of the installation 2018 were realized in China because of the Top Runner program. In total, there were about 2 gigawatt installation in 2018. Then in 2019, total installation of 5 gigawatt were shown. In 2020, we believe that most of the installation will be realized in the US because of the non-existing import taxes on bifacial products, but also in China and the MENA states we will have gigawatt installations. So the bifacial module from the very beginning in 2015 looked very similar to a monofacial one, only that the backsheet was missing, which was replaced by glass, but actually the junction box was still a big one, shadowing some solar cells, also not very optimized. So here you can see the La Hormiga plant, which consisted of such old modules, Bison modules produced in Italy at Megacell, and Franco Traverso was constructing this at the time largest bifacial PV plant, also using white reflector on the ground, so white pebbles, in order to enhance the albedo. If you look at the bottom of this installation, you can see the old modules where the junction boxes are covering the cells. But what is also remarkable is that there is no soiling at all, so there is no coverage of dust of the rear side. Even the front side is covered by dust. So actually Franco was not cleaning these modules for 10 months, but the rear side was really unaffected by soiling, which was very remarkable at the time. On this slide you can then see the state-of-the-art bifacial module, which you can see these days. You have these white reflectors in between half-cut cells, and this technology was extremely important because then on the front side you had the same watt as for monofacial modules, so the same power. That means you didn't have to cannibalize the front side power of the bifacial modules. And so normally these days we have bifacial modules with frame, then using double glass but also transparent backsheet are entering the market, then shallow junction boxes or split junction boxes for N-type. We have polyolefin, and we have N-type cells, or mostly still PERC bifacial solar cells, having then 5 to 6 bus bars or multi-bus bars, and as I told you before, half-cut cells. Coming now to applications of the bifacial PV market. So for utility scale, industrial and residential flat roofs and building integration, we have different geometry of installations, for example in fixed tilt for all three categories, but also we have vertical installations which are becoming increasingly important also because you can broaden the fit-in peak. You have more electricity in the morning and in the late afternoon. But what is becoming extremely important for utility scale is the combination with horizontal single-axis tracking. Now, what is influencing the bifacial gain? First of all, of course, the albedo is important, the reflection of the ground and surroundings, but of course also modules bifaciality, which can vary from 0.6 for PERC modules, for example, or close to 1 for top-con and heterojunctions. Then we have installation geometry, for example, the height of the module edge from the ground, and then row distance, the so-called ground coverage ratio. And also the latitude is important, what kind of direct or diffuse irradiation you have. So coming now to bifacial benefits and risks. Coming now to the bifacial benefits and risks. So benefits, it's quite obvious. In total, it's the higher energy yield that you can obtain with bifacial modules. And if you are installing bifacial modules on a horizontal single-axis trackers, so in average, for example, if you have a albedo of 30% in the desert and installing PERC modules, the average gain is about 10%. In addition, you have the tracking gain if you compare to fixed tilt installations. So in total, you have an electrical gain of, so energy gain of more than 30%, 32%, which is a no-brainer to use bifacial tracking. In addition, you have different generation curve shaping. For example, if you are installing vertical systems, you have more electricity in the morning and late afternoon. With that, you have also very low ground coverage ratio, so you can have a double use of the land. Agro PV is quite interesting for that. Then, of course, nice appearance. And if you are using fixed tilt in snowy regions, then also the snow is melting faster from the front side, and you have generation all the time from the rear side. So now coming to the risks. One of the risks is, of course, overestimation of the yearly yield, which was quite a problem in the past, and that for the bankability was not that good for bifacial modules, that or bifacial systems, that there were not reliable simulation programs out there. And but at the moment there are a couple of them. So for example, also PVSYST is working quite well. We have our own program called MobyDick. There's a Great Eye from TNO and Sam from NREL. So energy yield simulations are existing, but still we need more experimental data to verify the simulations. Then the question is about the maintenance of the system. Do we really need a better maintenance, for example, cleaning of the rear side of the module, or if you enhance the albedo in the desert, will that be covered by sands? Do we need the maintenance of the ground albedo and things like that? But what is also important is adding complexity to your modules also leads to higher possible degradation of bifacial modules. For example, LE, TID, PID. So you have, for example, also what can happen. You could have a rear side finger degradation and the transparent backsheet. If you are using such backsheets, they can degrade. So in total, we need better testing for bifacial modules, but this is what is offered from many institutions now, for example, from PVEL. At the end now, I will show you a couple of slides about some degradation mechanisms which are important for bifacial modules. So on the left-hand side, you can see a monofacial module and a monofacial PERC with a closed aluminum surface on the rear side, and on the right-hand side, you can see then a bifacial module and a bifacial PERC. And you immediately can see when you are opening the aluminum on the rear side, then the dielectrics gets visible, and there, for example, an additional effect can happen. You can have a rear side potential-induced degradation. And if you are using different processing sequences in your PERC process, then of course LETID and many things could appear in addition. So in total, as I told you before, more complex and high efficiency technologies have higher potential for degradation. But if you understand your process, this might not be a problem. Coming now to the degradation mechanism that everybody is fearing, because it's extremely difficult to understand, and actually it's quite complicated, so nobody is understanding it in detail. It's a so-called light and elevated temperature-induced degradation, and it consists of 3 different degradation mechanisms. Mostly it's LID, light-induced degradation, hydrogen-induced degradation, and passivation degradation. And if you understand your process, then you can actually produce solar cells without LETID, but you have to take different measures, for example. Because of LID, it's a cause of formation of boron-oxygen complexes. Then you have to take care that your material is low in oxygen. You can use high resistivity material, or, for example, go to gallium doping, and this is actually what is happening now, that most of the wafers are now gallium doped. For hydrogen induced degradation, you have to optimize your process so that actually not much hydrogen is penetrating into your system, and you have to adapt, for example, your firing temperature and things like that. So if you understand the process, then there is no problem. You can also use a post-treatment of the cells that actually you are running through the degradation curve, and at the end you can stabilize your solar cells. The material, p-type material, is becoming a better quality, and if you understand your hydrogen kinetics in your system, that everything is okay. On this slide then you can see what can happen when the modules are not LETID free. So you will see a decrease of your power in your system, in this case 8%, and after a while these modules will regenerate again, but this can happen within, let's say, 2 or 4 years. It will be a disaster, because then you have less power in the early years, which can ruin your business plan. So a better testing of the modules is required. But as I told you before, there are modules out there from producers that actually understand the cell process. So LETID, let's say, should not be a problem in good modules. Maybe you remember about 10 years ago, there was a big issue with potential-induced degradation when every module producer had to go cost down using low-cost encapsulants. And the problem is solved now for the front side and well understood, but for bifacial modules, because you are opening the rear side and the dielectrics also get visible there are other effects now popping up. So for the front side, it was mostly PIDS, which is shunting potential-induced degradation caused by shunting the junction by sodium ions mitigating into the stacking faults on the front using shunts, causing shunts. But then PIDP is now observed, which is polarization type of potential-induced degradation, where you are losing the passivation ability of the silicon nitride on the rear side. But here again, if you are using good material in your system, for example, polyolefins, this should not be a problem. Coming now to the summary and conclusion and outlook. So we have seen that bifacial technology offers an increase of energy yield at low additional cost. So it's a no-brainer actually these days to use bifacial systems to lower the LCOE. Bifacial PERC at the moment is very strongly dominating the market, but it seems that this technology is coming to its efficiency limits. So there is now room for N-type solar cells and also better P-type materials, so gallium-doped PERCs are now coming. Better module testing is required because, as I told you, adding complexity to your modules is then also adding the possibility of degradations, and also more reliable energy yield simulations are required. And I'm sure that with bifacial horizontal single axis tracking, we will reach soon, at least in the MENA regions, the 1 cent per kilowatt hour. In PV, everything is about reducing the LCOE. And you can see in this curve that it has been drastically reduced in the past 10 years. So now we are talking in average about levelized cost of energy of about 3 cents per kilowatt hour. And when we will use more and more bifacial tracking, that we can reduce it even faster. So let us move together to cost below 1 cent per kilowatt hour, which will be mostly realized by bifacial tracking. And with this slide, I would like to invite you to the conference in November to Korea in Jeju. I was asked to organize a bifacial session during that conference, and there we will discuss mostly the new developments of bifacial cells and modules. And with my last slide, I would like to already invite you for the 2 coming events for next year for bifacial PV. The first one will be in January in the Bay Area, and the second one most likely in October in Chile, in Antofagasta. So thank you very much for your attention, and I'm ready for questions.